Swayam Prabha. Digital India. Educated India.
Hello friends, I hope all of you are well, and I am sure you have already gone through the previous 3 lectures. I hope that you have understood the concepts that we have discussed there. If something is still not clear, if you want some more discussion on any particular concept, please write to me in the portal. I will try to respond at the earliest to them. Now I was having a quick revisit to the earlier 3 recordings, and I have found that I started a bit shakily in all the 3 lectures and settled down only after 10-15 minutes. Let me try to change the trend a bit in today's lecture. My initial plan was to take 3 lectures on this first module in this first week on the topic of introduction to measurement, but as we are trying to add several or connect several different concepts or components related to this topic of measurement in this particular week itself, so I decided to take a 4th lecture so that we can have some more time and go through gradually in different concepts. Now what we have discussed so far, by that time, as you have already studied the earlier 3 lectures, you are introduced to the significance of measurement. You have learned about different levels of measurement like nominal, ordinal, interval, and also the ratio levels of measurement. Then you have learned about different methods of measurement, different modes, basically direct and indirect mode, null, difference and deflection mode. And then we have discussed about the structure of a general measurement system, and from there we know that any measurement system, simple or complicated whatever it may be, generally has 3 completely different or identifiable stages. There is one input stage which creates some kind of interface between the physical device and your measurement system. It receives some input signal from the physical device, generally also receives another input signal from a so called standard, and then a difference signal or so called transduced signal is supplied to the second stage. The second stage is a signal conditioning stage, where the transduced signal goes through one or multiple levels of alteration like amplification, modification to some other form of energy, etc. Sometimes if some feedback kind of control is required, then a control signal is also sent back to the input stage from this signal conditioning stage itself. At the exit of the signal conditioning stage, we get the desired from the output signal, and finally we have the output stage. In the output stage, it receives the signal from the signal conditioning stage and then creates an interface to the recording device and gives us the output in whatever form we want, a display on a screen or maybe a printout of the observations or anything else. Now, as any simple measurement requires the interaction between so many different components, there is always probability of having some kind of errors or inconsistencies or inaccuracies creeping into the final output that we are getting. And like we have already seen examples in the previous lecture, even calculation of very simple quantities also may involve 3, 4, 5 different measurements. Like just to calculate the power dissipation required by a domestic water heater or maybe a room heater, we all have to measure maybe the current, maybe voltage, several resistances, something like that, or maybe just to measure the flow rate of water through a domestic water supply, again we may have to go through 3, 4 different measurements. And when we try to combine all these values in a suitable functional form to get the final output, then the inaccuracy, small value amount of inaccuracy present in each of them can get multiplied and or can get combined into some suitable following some suitable pattern, giving us a much larger amount of error which may be quite significant. And that is why it is very important to understand the different kinds of errors that can be present in any measurement system and how to get an estimate of that. That is why instead of having just one, I am taking 2 lectures on this error estimation thing. Whenever we are talking about any kind of experiment, any kind of measurement, this measurement error analysis or so called uncertainty analysis is a must, and that is why we need to have a clear idea about how to perform the uncertainty analysis and also how to identify the uncertainty present in the output of an individual instrument at the very beginning itself. Because in the next week onwards, or rather in later weeks when we shall be talking about particular instruments, we always have to look for corresponding uncertainty values. Like we have discussed in the previous lecture, there are 2 broad kinds of errors that we may find in measurement. One is systematic error, which generally is associated with very common terms like zero bias error, zero drift, sensitivity drift, etc. Measurement errors can be quantified. We can easily identify their source, and therefore, via the process of calibration, we generally can identify the, or generally can eradicate or at least minimize the amount of systematic error from a final measurement. The effect of measurement effect of systematic error generally is to move the final recorded values into a certain direction or provide some kind of bias to the output, and that is why they are quite commonly also referred to as bias errors. The other one is a random error. Random error is difficult to identify from the source, very difficult to quantify, and they are, as the name suggests, very much random in nature. Like using the same instrument, if we want to measure the same variable several times, because of the presence of random errors, we may get different values. So, random errors basically affect what we call the precision. That is, because of the presence of random errors, the different observations of the same quantity may get scattered around some kind of mean, thereby affecting the precision of the final output. That is why random errors are also referred as precision errors. So, systematic errors are also called bias errors, and random errors are also called precision errors. While systematic errors or bias errors affect the trueness of the final value, random errors affect the precision, and these two combined affect the final accuracy of the observation. Like the example that we have seen in the previous lecture, when a system is having high precision, that is very low or minimal random errors, but some kind of accuracy related issue or trueness related issue because of the presence of bias error, you may find all values are forming, all output forming a nice clubbing, but actually away from the final reading. So, we are having some kind of systematic error present, but there is no random error. Similarly, when the system is not having any kind of systematic error, that is a highly true output that we are getting, but random errors are present, then we may find that all the observations are well scattered and generally scattered around some kind of mean, which may be somewhere here in this particular example. Both the errors can be present simultaneously in the system, and that is the generally most practical case. We always want our result to be both both highly precise and also true or accurate, but that is a very ideal situations. Most often than not, we have to deal with this particular scenario, that is, it is neither precise not very true, thereby affecting the final accuracy of the observation from both bias error and precision error point of view. And the total error that can be present in a measurement is a combination of both. We have already seen that there are several ways we can represent the error present in a final reading. Say for example, if we are using a pressure gauge which is giving us a value of say 100 kilopascal. Now, the inaccuracy present in this can be reported in several ways, like one particular way of representing the error is, the most common way is plus minus 1%. It indicates that while the instrument is reporting a value of 100 kilopascal, but actual value may range between may be anything between 99 to 101 kilopascal, that is plus minus 1% of whatever we are getting. Actually, whenever we are getting such kind of plus minus some percentage or some fraction, be careful about the details about this. Most often than not, this one refers to plus minus 1% of the value, but there may be several situations where actually it is given as plus minus 1% of the full scale of your instrument. That means, suppose the same pressure gauge can give you a reading up to 400 kilopascal. So, its full scale or the maximum value it can record is 400 kilopascal, and if it is having plus minus 1% error of this full scale, that means actually the error that it may encounter is 1% of this maximum value, that is plus minus 4 kilopascal, and that is fixed for any kind of value that you are trying to measure. That means if you are trying to measure, or if your output is something like say 50 kilopascal, then also there is possibility of having plus minus 4 kilopascal error, or if your output is 250 kilopascal, there also you may have the same amount of error creeping in. So, when it is given as plus minus 1% of the full scale, then we have to consider this fixed quantity of error. However, if this full scale part is not mentioned, then the quantity of corresponding error will keep on varying with the output. Like when the output is 250 kilopascal, then it will be plus minus 1% of that, that is corresponding error is 2.5 kilopascal, whereas if your output is just 50 kilopascal, it is 0.1% of, sorry, it is 1% of that, that is 0.5 kilopascal. And the other kind of way of, so this percentage is one way of expressing the error rating of one instrument, and the other one is we have also seen, like it is also possible your instrument is having a fixed error of 5 kilopascal, where the error is given in terms of absolute quantity. So, any value you take, that is always you have to consider this 5 kilopascal of error on either side of the measured quantity. This is quite similar to percentage of full scale. That means there are three ways you can get the error specified, like the examples that we have discussed. One possibility is plus minus some percentage of full scale, which basically leads to a fixed quantity, whatever is the range of your instrument or the maximal output you can get, it is 1% of that is fixed. You can get plus minus 1% of your reading, that is recorded value whatever you get. So, it will keep on changing on what you are measuring, or the other one plus minus 1% of an absolute quantity, like say plus minus 1% of 5 kilopascal. So, both these two will lead to a fixed quantity of output in any measurement independent of the measured quantity being small or large, whereas this one will keep on varying. Error will be small for small output magnitude, it will be large in larger output magnitude. But I come back to this particular one. Now, in the previous lecture we have discussed about how to identify the uncertainty in a final measured quantity, or I should say when we are trying to combine several measurement in to get one particular value, one particular calculation done, then how to calculate the final error error in the final quantity. There intentionally I mentioned that the estimation of systematic errors, but I would like to correct that now. I intentionally did that just to avoid any kind of complexity. Actually, what we did there, that is the estimation of this total error. This WR is the total error, not systematic or bias error or precision error separately. We actually estimated the total error present in the final calculation. And also, if you look carefully, like the examples that we have discussed, in all the cases we never talked about any individual instrument, rather we talked about getting observations from several instruments and then combining that to get some theoretical calculation done for a separate quantity, like calculation of power when we have the measured value of current and voltage available. So, what we did there, that is commonly referred as propagation of uncertainties in a final measurement. Like we have some uncertainty present in the current value that the corresponding instrument has given, we have some uncertainty present in the voltage value that corresponding voltmeter has given, and now we are combining them to get a measurement of power or a calculated value of power, and following the method that we have discussed, that will show us how the uncertainty present in both the individual measurements, like in power like in current and voltage, will affect the finally calculated value of power. So, what we did there, that is basically the propagation of uncertainties in the final value. We are going to see about how to estimate the precision error for a particular measuring device in today's lecture. But before that, this bias error or systematic error we are not going to talk about, because they generally appear because of wrong calibration or wrong information provided by manufacturer, or maybe you are having a correctly calibrated instrument, but with long period of use or with wear and tear, it may develop some kind of bias error. So, by repeated calibration or recalibration, we can eradicate or minimize the systematic errors. So, dealing with the systematic errors is a part of calibration process, and we are not going to talk too much about that. But precision error or random error are related to the measurement that we get, the individual measurements or a group of measurements. So, we are going to deal about this one today using some statistical knowledge. But before we do that, in the last lecture I left you with a couple of problems. This was one of them, and there was another one related to the venturimeter application. Have you tried to solve it? I request you, please solve it. If you have not done that yet, stop or pause this video here itself, go back to the earlier video and try to solve these two problems, so that you have a better idea about how to calculate the propagation of uncertainties, or how to estimate the total error that may be present in the finally calculated value. So, it is a request here. If you have done that, then please continue with this video, but if you have not done that, then I repeat, please pause the video here, go back to the previous lecture and try to solve these two problems on your own. So, here I gave you the answer. Here the problem was, you have a resistor where the values are given for its resistance. It is given as 10 ohm and plus minus 1% error associated with this. It is not mentioned that this is of plus minus 1% of the reading or full scale. If nothing is mentioned, then we are going to consider this as 1% of the reading itself. That is, 10 ohm is the value of the resistance, and so plus minus 0.1 ohm, that is actual error that is associated with this resistance value, is plus minus it is 1% of this 10 ohm, that is plus minus 0.1 ohm is the error that is associated with this resistance measurement. If it is full scale, then that has to be exclusively mentioned. There are two ways we can calculate the power dissipated across this. One using like we have discussed, one where we can just measure the current that is flowing through this resistor, and then we can calculate as I equal to I square R. Other way we can calculate is, we can measure the current flowing through it and also the potential difference or voltage drop across this resistor, and we can calculate power as P equal to E into I. So, finally calculated value should be same. Like if we follow the first method, what power value you are going to get? In this case, current is 10 ampere and resistance is given as 10. So, we are going to get, following the first method, it is 10 square into 10, that is going to be 1000 watt. Similarly, if we follow the second method, you have 100 as a potential difference into into 10 ampere as current, and that is again going to give you 1000 watt, which is the nominal value of the final power output. So, you may feel that both methods are equivalent, we can go by any of them. Definitely they are equivalent theoretically, but if you perform the uncertainty analysis on both the calculations, in the first case when you are following P equal to EI, that is this particular one, you will get an uncertainty level of 1.414%. I am giving you the value, please calculate this and check whether you are getting this one or not. This is what I have got through my calculation. It can be around that one also. If you are getting something between 1.3 to 1.5, that is fine, but any value either outside that range is there has to be something wrong with your calculation. Now, if you calculate following the other one, P equal to I square R, that seems much easier, because we here in this case we have to measure both the E and I, but if we follow the second method, we have to calculate only the current. But here we are getting a higher, at least 1% more error or error possibility. That means, while this first case P equal to EI is going to give you an error margin of something like plus minus 1.41% of 1000 watt. So, it is going to give you something like 14.14 watt, whereas if we follow P equal to E square by R, I have done as E square by R. Okay. So, if we do E square by R, it is only using the potential. So, it is as E square by R, then it remains as your E was 100 square divided by R. Again you are going to get 1000 watt also, but corresponding error possibility is 22.36 watt. So, much higher error value, about 8 watt higher error prediction that you are going to get. So, this way we can identify which way to follow. Despite we need to do two measurements, it is always better to go for this, measure both potential difference and current, and accordingly measure the power. And there's another problem was given for venturimeter. Again there are 5 different parameters which can 5 different measurements that we have to do to get the final value of mass flow rate of air through the duct. So, for we have to calculate basically 5 quantities, for each cases try to calculate the product of sensitivity and corresponding uncertainty. Like for this coefficient of discharge, this is the sensitivity, this is the corresponding uncertainty. Similarly, you can get the product for all the 5 quantities, calculate their value, and and finally calculate the uncertainty. If you do calculations properly, you will find that the measurement of this inlet pressure or the contribution of inlet pressure will be around 71 to 72% of the final value, whereas that for this coefficient of discharge is about 21%. That means the final uncertainty that you are going to get, 93 to 94% of that will be taken care of by only these two. Others are having much smaller contribution to the final error. So, that provides us a way of tackling or choosing our instrument. Like in the previous case, previous example, we have seen a way of identifying the measurement method. Despite we have to measure two quantities, it is better to go for the both voltage and current measurement instead of only voltage measurement, whereas or only current measurement also. Whereas in this particular case, we can see there are 5 quantities where some uncertainty we are getting, but instead of looking after or trying to improve all 5, if we look at only this particular quantity, that is if we look at reducing this particular uncertainty, then we are going to get the largest gain in the final output. And once we are able to handle this inlet pressure measurement, then probably we should look at this CD, the coefficient of discharge. And if we can reduce the uncertainty in both these quantities present at least to the half of the given value, there will be a drastic reduction in the final uncertainty present in final mass flow rate calculation. So, there is no point going for improving the uncertainty in this area measurement or this temperature measurement. We can always do that, but the effect on the final mass flow rate will be very small, because much more significant effect is coming from this inlet pressure and the coefficient of discharge, and we should look into them first. So, this way we can identify which are the most vulnerable instruments in a particular measurement system. Like in this particular case, the most vulnerable instrument is your inlet pressure measuring instrument, and we probably have to try a better instrument which has much smaller level of uncertainty. Please try to solve this problem. Now, let us move on to check the random errors. Now, random errors, as the name suggests, again they are very random in nature. Like in a particular quantity, if this is your true value like shown by the red arrow, and you are getting your measurements restricted within this zone with a mean like this, then this actually is a measure of your systematic error. The distance between the true value and the mean can provide you a way of measuring the bias error. Problem is that we often do not know the true value of your measurement. If you are trying to measure an unknown quantity, you can definitely get the mean from a set of readings, but we do not know the true value, so we can't estimate the systematic error. Only if we know the true value, then we can estimate the systematic error, which is the process of calibration. So, via the method of calibration we can always eradicate. Now, once we have the mean, the precision errors will lead to this random fluctuations, which you can see here. The readings keep on fluctuating on either side of the mean over some suitable domain, and you can just check any random value, like this is one particular set of reading, and immediate next reading we are finding somewhere here, and immediate next one is somewhere here. So, there is over this range of data set that have been collected, there is significant amount of random error that is present, and because of this random nature, we can treat them only by some kind of statistical measures. So, some very fundamental statistical definitions which all of you are definitely aware about. Let us say we are dealing with n number of data. This capital N refers to the total number of data that we have collected or we can collect in a certain situation. Then arithmetic mean refers to the average of all these values, whereas geometric mean is refers to this quantity. We shall not be using geometric mean, so I am not talking about this. And the standard deviation talks about the average deviation. Like the deviation di in a particular measurement is xi minus xm, where xi refers to the measured value and xm is the mean which is shown there. So, standard deviation basically talks about the summation of this di square divided by n, the total number of reading, whole to the power half. This is what is standard deviation, gives us a way of measuring the total amount of deviation that can be present in a reading. But to use these definitions of mean and standard deviation, or to use them for further statistical processing, we actually need to have a very large value of n. And practically in industrial measurements or in engineering measurements, often we don't have the option of going for so many measurements. Rather, what we do is sampling. Sampling is this. Like suppose we want to know some characteristics of this huge population or huge number of data points that are possible. As it is not possible to handle with so many data, so we just take some random samples from that and try to do all the calculations based upon that. And then whatever observations or whatever conclusions we get from our statistical processing on this sample, we try to get that back to the population to get some kind of conclusion about the population. This is what we measure, what we call as sampling. Now, the definition of standard deviation that we have provided earlier, that refers to very large value of n, basically the number of number of parameters or number of data points available in your population. That is why this definition is often referred as population or bias standard definition. However, if we restrict our calculation only to the sample, then for the sample also we can calculate a mean and a standard deviation. Problem here is the value of this mean for the sample x bar, what we are going to get, that may not be equal to the arithmetic mean xm, because that will depend upon your choice, the choice of your sample. Say we are trying to measure the value of okay, let me take an example. Suppose we are trying to measure the pressure of steam that is going out from a boiler and going towards a turbine. Now, we are trying to monitor the pressure value, and that we can do using any suitable pressure measuring instrument. We know that pressure can be measured at every time interval. So, depending upon the resolution and time stability of your instrument, you can measure the pressure after every 1 second, after every 1 millisecond, after every 1 microsecond, thereby providing an infinite set of data. But practically it may not be possible to handle so many measurements. So, instead of measuring so many data, we decided to measure just 10 or 12 pressure values after every 1 second. So, we have 12 values of pressure listed in a table like this, where we have a pressure value at every point. Now, the value of this x bar that we are going to get depends upon which values that you are going to get. Like suppose your pressure is varying with this way, plot time on this axis, pressure on this axis. So, pressure is varying in this way. Instead of taking such a continuous measurement which will lead to the population and an infinite data set, we are taking sample at certain points. So, if you take sample 1 here, another here, another here, then what mean or what value of x bar that you are going to get, p bar in this case, the average pressure. If your choice of pressure is this one and this one, your choice of sample, then the value of x bar may be different. That means the value of this x bar is dependent on the chosen sample and dependent on the total number of samples small n that you have collected. So, this x bar may vary with sample, and as the number of samples, that is as the value of this small n keeps on increasing, this small x bar approaches the actual arithmetic mean. That is when small n approaches capital N or tends to capital N, x bar tends to xm. Similarly, the standard deviation, definition of standard deviation also should include n, but instead of n we are using n minus 1, because here in the denominator we have the degrees of freedom. While dealing with the population, degrees of freedom is equal to the total number of data points, because the value of xm is independent of total number of data points. But while dealing with the sample, the value of x bar is dependent on the value of small n. So there is 1 degree of freedom that is less, that is basically one kind of restriction that we are putting the number of data points, and that is why we have degrees of freedom as n minus 1, and this is called sample or unbiased standard deviation. So while dealing with a smaller sample, we generally go for this x bar and small s. So this is what is your population, a very large data set. From there we have randomly selected a small data set. From the small data set we are calculating the sample mean, the sample standard deviation, we are drawing some inference from there, applying the statistical measures, and then we are trying to project that to get the population mean, population standard deviation, and some other parameters about which we want to get some kind of idea. We could have got that directly from the population itself, but there we have to deal with a very large data set, that is why we always do with a smaller data set in the form of sampling. And if the choice of sample is proper, then whatever you are getting from here, you should get the same thing from here also. However, if the choice of sample is not proper, then these two may differ from each other. So sampling itself is important, which samples to take, and also it matters which kind of statistics you are applying on the samples. Let us take one example. Here I have provided you a set of data for some students appearing in an exam. There are 100 students in a class, and each of them has got some kind of marks in the exam. Exam was conducted out of 100 as well, and instead of dealing with individual marks of all the students, we have identified 10 different groups. The first group refers to students who have got marks between 0 to 10. We can see there are 2 students who have got that. Second group refers to students getting marks between 10 to 20. There are 3 students getting that. Similarly, going above this way, we can see between 70 and 80, 17 students have performed, which is quite good, and between 90 to 100, the highest category, the best category, only 3 students have got. So we have got we have decided on 10 different groups, 10 different intervals often referred as, and we know the number of samples present in each of those intervals. Now if we represent them in a column chart like this, where each of the column corresponds to one of the groups, like this one corresponds to this particular group, this one corresponds to this particular group, this number 13, and accordingly we can see between, from the chart also it is, from the initial data table also it is shown, between the 60 to 70 the maximum number of students have got the marks, and on either side of this we can see a nice distribution, that is the number of students appearing in a group is highest here, then is decreasing on this side, it is going down on this side as well. This particular kind of diagrams are known as histograms, which gives us a quite good estimate about the characteristics of or number of samples appearing in each interval. Here we have only 10 groups or 10 columns appearing in the histogram, but we can easily increase the number of columns using the same data set. How we can do that? Like instead of taking 10 intervals, if we take more number of intervals, let us say we decide on the groups like now how many students have got between 0 to 5, then between 5 to 10, then between 10 to 15. That means this way instead of 10 we can have 20 intervals. So we can have some numbers appearing in each of them, it may be 0 in some, it may not be 0 in others, and accordingly we can again get more number of columns appearing in the same histogram, 20 columns at least. So even a better representation for this. And if we break it into even further, that is treating each number separately, how many student has got 1, how many student has got 2, then there will be 100 intervals appearing on the same thing, thereby giving an almost continuous representation of this particular graph, is not it, where we are just trying to plot the samples on or the intervals on the horizontal axis and number of students appearing in each interval on the vertical axis. Then as the number of interval increases, it approaches the nature of a continuous curve. Sometimes instead of dealing with the individual numbers, we deal with fractions. Now here what this table represents, can you guess from the values? Like the first one, that is up to 10, we can see 0.02 represents just 2% student have got below 10 or up to 10, then 5% student have got between 10 to 20? No, this is below 20. Similarly, 72% student have got marks below 70. That is, this is a cumulative sum that we are doing. And if we plot that with respect to your samples, then we can see a nature like this, which is known as cumulative frequency diagram. This represents the cumulative frequency that is appearing. Like if we look at the diagram, if we plot a vertical line from here, then on this side the area under the curve here, or instead of drawing an arrow here, in the vertical axis if we plot the numbers of students, then we have this particular area will give you the total number of students who have got marks less than 60. Here as we are plotting fractions, then this is going to give us some idea about number of students who have got marks less than 60. Similarly, when you reach 100, if we delete all this, if we reach 100, then all the students are inside this. However, the area under the curve is not going to give you total number of area of the curve under this curve is not be equal to 1, because that keeps on varying. It is a cumulative frequency only that we are dealing with. So, instead of dealing with cumulative frequency, we generally prefer dealing with individual frequencies. So, we are going back to the original table and just adding one column to that. Like here, there are 2 students in the bottommost group, and these are the percentage they are appearing there. Here we have 13 students appearing in the group 40 to 50, and that refers to 13% of the total data. So, here the third column, the values that are given on the third column, that represents the frequency of a student appearing in the corresponding interval. Like the frequency of a student, students appearing in a student appearing in the interval of 20 to 30 is 0.06 or just 6%. So, once we plot that with respect to the individual intervals, then we get a distribution like this. It clearly shows at which interval what is the frequency of appearing. Like if we see this, then this refers to something like this. Actually, I have actually missed the bottom column, but or the horizontal axis here, but I guess this data refers to this particular one, probably, sorry, it refers to this particular one, correct. That means, if we have this horizontal axis properly denoted here, then we can clearly see within this particular interval, which is 80 to 90 in this case, the number of students appearing, or the probability of a student appearing in this particular interval is 0.08 or 8%. This particular diagram is called a frequency diagram, or often called the probability distribution, because this is giving only the probability of students appearing in a particular interval, or probability of a data point appearing in a particular interval. So, that takes us to something known as the probability distribution function. Quite often probability distribution functions are having a form like this, which are having a peak somewhere and generally decreasing on either side. P is the probability distribution function, then the total probability of a data appearing between this A and B is just the area under this particular curve. And so, the probability of all the data points appearing under this within the limit of x minimum to x maximum, that is a range of x, has to be equal to 1, because it encounters all the possible probabilities, or all the probabilities that a phenomenon can happen. Like you can think about, say you are given with a coin, an unbiased coin. Now, if you are tossing that coin, then what are the possibilities? You can either get one head or you can get a tail. So, there are only 2 possibilities. Now, if I provide you 2 unbiased coins and you are tossing them simultaneously, then what results you are going to get? You are going to get either 2 heads, or tail in the first, head in the second, or head in the first, tail in the second, or you can get 2 tails. So, there are only 4 possibilities. So, this way when you are tossing number of coins, we can combine all of them to get the probability of a particular combination appearing this, and the area under the curve will give you the total number of probability. Like here there are 4 events that are possible, and the probability of each of them appearing is just 1 by 4. So, if we sum it up over all of them, that has to be equal to 1, which is given by this particular thing. There are several kinds of probability distribution function that can be defined. There are several that are used in statistics also, but in measurement purpose the one that is most commonly used is the Gaussian error distribution form, which is also called the normal error distribution form, because several natural phenomena also follows this particular kind of trend. It is a function of a form like this. Here sigma refers to the standard deviation, the population standard deviation, because here we are performing over a very large set of data, or when x tends to minus infinity to plus infinity, or ranges from minus infinity to plus infinity, that means our data set is an infinite one. And here this mu refers to the x m, I used x m earlier, this refers to the mean, the arithmetic mean or based on the population. So, this is the Gaussian error distribution. Quite often we transform the Gaussian PDF into more convenient form using a variable z, such that z equal to x minus mu upon sigma. So, if we put the expression of z there, then we get a modified function p prime z, which is having a form like this. A range of z can be defined based upon x itself, but as x ranges from minus infinity to plus infinity, z also will be ranging from minus infinity to plus infinity. Now, the probability that a certain data point falls within a specified distance x1 from 0. Before doing that, if we see the Gaussian distribution as the range of x is minus infinity to plus infinity, the plot of px will be somewhat like this. And this is your x, we are going to minus infinity on this side, plus infinity on this side, and this is x equal to 0 when we are having the peak of this curve appearing. So, if we are trying to identify one point whether it falls within a certain distance x1 from x. So, your x1 can be measured in this direction and also in this direction. That means, we are talking about a band of thickness of width twice of x1, that is x1 on positive side and x1 on negative side. To identify that, what we have to do? We have to integrate this particular px over this interval, that is we have to integrate it over minus x1 to plus x1, and if we integrate this over this interval, then it being this particular curve being a symmetric one, we can take this 2 out, thereby changing the integration limits from 0 to x1, and then using this transformation of z, it comes to a form like this: 2 upon sigma root 2 pi integral 0 to z1 exponential minus z square by 2 dz, where this z1 is nothing but x1 minus mu upon sigma. Quite often z is also combined with sigma itself, or we get directly the measure of z1 upon sigma. Now, here I have marked out this particular portion in red separately, because of course, for any value of z starting from 0 to infinity, we can perform this integration easily and we can get the value of this integral, but it is not required, because people have already done this, and there are standard tables available for this Gaussian distribution, where the magnitude of this red portion is already available, like shown here. Here we can see the values of z given here. Here the z refers to just integration between 0 to z. So, we can perform integration in 3 possible ways. If we are trying to identify whether the value lies only on the right hand side, then what is shown here, that is the one. If our interest is to identify the probability of a data point appearing on the left hand side within a distance z, then we just have to do the same thing, but on the other side the probability also will remain the same. But if our interest is to identify not left or right, rather whether just what we mentioned earlier, whether it lies within a certain distance z, then we are basically trying to identify over this total quantity 2z, and hence the any value within this has to be multiplied with 2. Like suppose if we are trying to identify whether a data point lies within a distance z equal to 1.5 from the point z equal to 0 or x equal to 0, then for z equal to 1.5, this is the data probability. We can see the probability is 0.4332, and this being a two-sided probability, so we have to multiply this one with 2, thereby giving the final probability that we are looking for. As z keeps on increasing, this one approaches 0.5, so that the two-sided probability approaches 1. As you can see, for z equal to 3.9, it is equal to 0.5, and that means all the points will come under this. That means we can say the peak of the curve, which is the mean, once we can identify the z, we can clearly say that the data point will be lying within mu plus minus z into sigma, where the z is something that will be coming from the measurement values that you have. This particular thing is known as the confidence interval, and what is left out is called the level of significance. This is something that where we have first picked z equal to sigma itself, that is the standard deviation itself. If you perform the integration, I am going back to this particular curve. This is z equal to sigma. You can see it is 0.3413. So, 34.1% of the total data will lie between your mean and mu plus sigma, another 34.1% will lie on the negative side. So, that is a total of 68 point something percentage of data will lie within a plus minus sigma distance from the mean. If we expand this to twice of sigma, then if we go back to the table, twice of sigma is giving you 0.4772. So, if we multiply with 2, we can see that 95.4% of all the data will lie within a plus minus 2 sigma of your mean. We can keep on expanding this, like if we go to 3 sigma, it is 0.4987, that is 99.7% of data will lie within a distance of plus minus 3 sigma distance. That means, if your measured values are following this Gaussian distribution, then we can clearly say that, or we can confidently say that out at least 68% of all the measured data should lie within plus minus sigma distance of the mean, and 95.4% should lie within plus minus twice sigma distance from the mean. There is another way of representing the same. Sometimes they represent in terms of odd, like as 68.2% data are lying within plus minus sigma distance, that means the probability or the odd for a data to lie outside that is just 1 upon 3. Similarly, 95% data is lying within plus minus 2 sigma distance. So, the probability for a data point to lie outside that plus minus 2 sigma range is only about 5%, that is an odd of 1 out of 20, and that is for plus minus 3 sigma limit, it is 1 out of 370. That is, once we expand our range to plus minus 3 sigma, then hardly any data will be left out. Now, the question is which one we should choose. That is depends on your choice of this confidence interval. Depending upon how strictly we want our data to be considered, we have to determine the range of observation. Like if we see that, if we decide that 2 sigma is the one that we should go for, then we can see that 19 out of every 20 data should be lying within our range, and then we can take this plus minus 2 sigma or as our limit of operation, or any z value also we can calculate. So, once a data set is given, then we can calculate the z corresponding to all the points, preferably to the points which are showing the largest deviation from the mean. We can calculate the z, and then we can check the z with all these limits, sigma or 2 sigma or something, and then depending upon our choice whether should we at all consider that data or not, we have to make some kind of decision. One particular criterion was specified by Chauvenetz. It is a very strict criteria. His idea was, if any data point is showing a deviation more than 2 sigma, then that has to be some kind of blunder or some kind of random points that is coming in. So, that should be discarded during the final processing. So, any data point which is showing this particular thing, that is di upon sigma greater than 2, or I should say the absolute value of di, that is mod di upon sigma greater than 2, then we know that 95% of the data should have d upon sigma less than 2, but only 5% data can show this kind of criterion and should discard them, thereby causing a change in both your value of x mean and your corresponding sample standard deviation, and thereby providing a much better measurement. Here we take a sample like that pressure measurement example that I have mentioned about. Here we have measuring the pressure 12 times, our objective is to maintain a pressure of 400 kilopascal, but from our reading we are seeing that for all of the 12 we are not getting 400 any of them, but they are fluctuating on either side. So, we calculate the mean and standard deviation. Mean is coming to be 400.8 kilopascal, standard deviation is 2.67 kilopascal. I have not mentioned the units here, but I should have. Standard deviation is 2.67 kilopascal. So, we can plot the Gaussian curve to check whether they are which ranges they are following, but which point he is having the largest deviation. Let us check whether for any of the data point need to be discarded during the final calculation or not, that we first have to check. Now, to check that which point is having the largest deviation, let us calculate the DI values. We have calculated the DI values, that is xi minus x mean, where DI refers to your xi minus x bar, because here we are talking about a sample. So, we are having this DI, and once we get the DI, then we are estimating DI upon sigma. So, this is the value of DI upon sigma that we have. This is a table of DI upon sigma that we have, and we can it got shifted a bit actually, all the data points. You please try to identify the correspondence, like this one should correspond to this particular case, and all got shifted in a way, probably some problem with the software that I am using for this data processing. Now, which one is having the largest amount of deviation? If I go through it, okay, this one is having the largest deviation of 4.69, largest deviation is 4.69 kilopascal. So, let us compare this. Even for this one also, you can see that the D upon sigma value is less than 2. So, there is no point discarding this data. We can continue this particular data, and now using this we can calculate the Z from this. Z comes to be 1.76. What is the relation for Z? For any particular value of Z, how we calculated? Z was x minus mu upon sigma. So, from there we can calculate Z to 1.76. Now, we try to identify the corresponding value of the probability. Z is 1.76. So, in the first column of our table we have Z, and here we do not have 1.76, but we have 1.7 and 1.8. So, we have to do kind of interpolation. Our 1.76 is lying something in between. So, the probability will be something in between these two. We have to do an interpolation between that, and correspondingly we are seeing that the probability is coming out to be 0.91776. So, which is a quite good value to have. So, where we can conclude that the data has a confidence interval of 1.76 sigma, that is all the data points that we have accumulated during the measurement lies within plus minus 1.76 sigma distance of the mean, and there is no need of discarding any data, and finally we can represent all this data as somewhat like this. This is the mean, sample mean, and this is the corresponding error that we can expect. So, the table of data that we have comprising of 12 pressure readings, that is having a mean of 400.8 kilopascal, and that is having an error of 4.69 kilopascal, and at this particular case, this particular example, this error of 4.69 kilopascal is not a very significant one, because it is coming well within that plus minus 2 sigma limit. Next, another test that I will cover very quickly. Of course, we can compare any data set with the Gaussian distribution this way, but we have to know whether this data set at all fits the Gaussian distribution or not, and that is generally done by the chi-square test, which is also a test for goodness of fit. Here this chi-square is given as the summation over the observed value minus expected value whole square divided by expected value. Here small n refers to the total number of samples we have, and another term is defined as the degree of freedom, which is n minus k. Here n is the, as I mentioned, total number of sample we have, and k is the number of conditions that we are imposing. When chi-square is equal to 0, then your observed and expected distributions match exactly. Like if we expect our data set, your observed will be coming from whatever our measurement device is giving. Expected is what we want. Like suppose if we go back to the example of that pressure reading, our expected value is 400 kilopascal for all of them, but observed we are getting something else. So, accordingly over this set of 12 data, that is small n equal to 12, we can calculate the chi-square value. If chi-square equal to 0, then that is an exact fit. As the chi-square keeps on increasing, that shows an increased discrepancy between the observed value and the expected value. And if the chi-square is larger than a certain predefined limit, then we can't go with this particular set of observation. But before the degrees of freedom, as we have used in the previous case, like when we are deciding on n equal to 12, there itself we are putting one restrictions in terms of this total data set. So, your degrees of freedom in this particular example will be 12 minus 1, that is equal to 11. So, we have a data set from where we can calculate the chi-square, we can also calculate the degrees of freedom to be 11. And now we have to refer to that chi-square table. These tables are very standard. I shall be trying to provide you some standard table, but you can get these tables on internet itself. Here is the chi-square table. Here first try to see what we have. On the first column we have the degrees of freedom, and in the table you have the chi-square values, and on the top horizontal axis we have the level of the confidence interval which we want. Look at this particular situation. In our example we have degrees of freedom equal to 11. So, we have to take a look at this particular x square values or chi-square values. Now, we have to decide what level of confidence that we want. If we want our data with a confidence level of 9.9, that is we want our data to fit the Gaussian distribution 90%, or not, I should not say Gaussian distribution, fit the expected distribution 90%, then the chi-square value that we are calculating, that should be smaller than this one. I repeat, some chi-square that we have calculated from our measurement, we have to compare that with the value that is given in the table. For that, first we have to identify the degrees of freedom, like in our case degrees of freedom is 11, and then we have to decide on some kind of confidence interval, what level of match we want. So, here 0.9 is the confidence interval that if we decide on, then corresponding chi-square value given on the table, chi-square limiting value is 5.578. If the value that we are getting from our data set is coming smaller than this, then we can go for the decided distribution. If it is larger than this, then we have to identify some other distribution. So, I would request you to try to calculate these values, check with expected value 400 kilopascal and also with Gaussian distribution, and see what values you are getting. Now, one final test. There are infinite statistical analysis that we can show, but I have a limitation of time and there is no need for also from the point of view of our course. So, just one final thing, where the standard deviation of the mean. As we have seen, depending upon our choice of sample, the mean itself may have some kind of variation. When the sample size is very small, the standard deviation is given as a formula like this, where sigma is the standard deviation corresponding to your population, small n refers to the number of data in the sample, and this is the standard deviation in the mean itself. T is a parameter which is given by another statistical test called T test. So, T is equal to your xm, which is the standard deviation, which is the mean that you are getting from population, that we have also used the symbol, we have also used the symbol mu earlier. I should have used the same symbol, but as I have mixed this up, please note that xm and mu are same, and x bar refers to the mean that we are getting from our population, from a sample. xm refers to the population, x bar refers to the sample, and using this T test we are trying to get an idea about the standard deviation that is present in the mean itself. This is particularly useful when you are dealing with a very small sample of data like n less equal to 10, which is very relevant in several practical cases, because generally in practice we do not have the option or time or even requirement also to go for very large sampling. So, we can deal with very small level of samples. Here we have again a data set like this. Here what your T provides is again the degrees of freedom on the first column and your confidence interval on the axis, on the, like, just take a look at this particular row. We have the confidence interval, and then we have the corresponding T values. If we go back to our example, there we had mean as 400.8 and standard deviation as 2.67. So, if you put that, then, and degrees of freedom was 11 as we have already discussed. So, if you put that, degrees of freedom is 11. So, this is the line. If we decide a 90% confidence interval, so this is 90%, in 90% confidence interval our T is 1.3634. So, that gives us a deviation of the mean of 1.05 kilopascal. So, here the mean pressure can be estimated with 90% confidence as 400.8 kilopascals, which we have already done, plus minus 1.051 kilopascals. So, this t test allows us to allows a way of calculating the mean itself, and once we know the mean, then we can go for the recalibration process to identify the standard bias present there. These all are related to the randomness or precision error that can be present in the measurement, and this mean itself is associated with the standard bias. So, in a sampling process following the t test, we can also identify the error that can be present in this mean itself. Now, from this measurement course point of view, you may not need to go for so many statistics. These are more from your information point of view. Whatever we have covered today, it is important just to know the concepts like the Gaussian distribution, how to get that, what are the needs of performing the chi-square test or t test, but I would not ask you to solve any problem on this apart from very simple examples like we have done here, and from just to give you some idea about to get some idea about how to deal with the random errors. But in this course, from the instrument point of view, we shall mostly be working with this WR only, which is a total error which combines both precision and random errors. So, from this point onwards, that is from the next lecture onwards, we shall be dealing only this total error. We shall not be talking too much about the bias error and precision error separately. Whatever error values that will be given either in percentage or in absolute, those will always refer to the total error. But the gist of the discussion that we had today, these are how to identify the values of those WR. So, this takes us to the end of our first week. So, in the module 1, we have learned about the significance of measurement, then we have talked about different levels and methods of measurement. You have learned about the structure of a general measurement system is different stages, 3 different stages basically. We shall be discussing about each of these stages later on. We have talked about the different types of inputs. The digital inputs is something of very importance, very large importance. We shall be talking about the digital inputs and its processing in the third module, and some more discussion about the output, about how to process the output, we shall be talking in the fourth week. We have talked about the static characteristic of a measurement system. There are several static characteristics have been introduced with the resolution, linearity are generally the most common one, and something actually I forget to mention, hysteresis, one property which actually is associated with a random error. So, that is another static characteristic which can lead to some error in the measurement. Dynamic characteristic is something that we shall be discussing in the next week as a part of module number 2. We have talked about the classification of uncertainties and how to deal with the propagation of uncertainties. And finally, we have discussed about different statistical treatment to get the idea about possible magnitude of random errors that can be present in our final measurement reading. So, that is the end of first module. Thanks for your attention. An assignment is already there on the portal. So, please try to solve the assignment. Whatever queries you have, I repeat, please send to me immediately so that I can respond. My TAs also will be continuously keeping a track of the portal to respond to your queries. In the next module, we shall be talking about the dynamic response of a system, and one topic that you probably can revise a bit before starting that is the Laplace transform, which is definitely you have it has been covered in your mathematical course in first or second year. Please revise the Laplace transform a bit so that in the next week we can start the dynamic characteristic of response systems. So, thank you.